Good morning. I am Dr. Niti Maheshwari, Assistant Professor, Applied Science and Humanities Department, Ajay Kumar Garg Engineering College. Now, I was discussing in my last lecture the molecular orbital theory. So, in continuation with my first lecture, this was my last slide where I was discussing the relative energy levels for 2s and 2p orbitals. So, the filling of molecular orbitals, they take place in two levels or two types. The first type is without big repulsion between 2s and 2p orbitals, where the interactions between 2s and 2p orbitals is minimum. And the second type, that is with big 2s and 2p repulsions, where these 2s and 2p orbitals, they interact with each other, and hence there is repulsion between the same type of orbitals, that is sigma 2s and sigma 2p, sigma star 2s and sigma star 2p. So, when there are less repulsions, then this sigma 2p, which is stable, it is lower in energy in comparison to the pi 2p orbitals. Whereas, when there are interactions between the 2s and 2p orbitals, then it becomes the pi 2p orbitals become lower in energy because of the repulsion between sigma 2s and sigma 2p, which leads to the stabilization of sigma 2s and destabilization of sigma 2p. Again, it leads to the stabilization of sigma star 2s and destabilization of sigma star 2p. So, as the energy of sigma 2p increases, this pi 2p becomes lower in energy. This is, I have shown how the filling of orbital take place with 2s 2p mixing and without 2s 2p mixing. So, in the case of boron, carbon, nitrogen, the filling of or the formation of molecular orbitals take place with 2s 2p mixing. But as the number of electrons increases, this effect diminishes and the filling of orbital takes place without 2s 2p mixing. That is the case which is seen in the case of oxygen, fluorine and neon. Neon, again, it does not form the molecule as its bond order is 0. Now, coming to the real world applications, generally the molecules, they are heteroatomic. So, how MOT explains the bond formation between heteroatomic molecules? What needs to be considered? The orbitals which are being involved, the electronegativity which decides the orbital energies, then the hybridization and mixing of orbitals. Again, the sigma bond which is being formed, it is formed by the additive combination and sigma star by the subtractive combination. And here again, the coefficient C, it indicates the contribution of the atomic orbitals to the molecular orbital. Now, in this case, when the two atomic orbitals they are combining, suppose it is when A and B atom they are combining, the wave function is psi A and wave function for the second atom is, or the atomic orbital is psi B. Now, when we were discussing about homodiatomic molecules, in that case the value of these coefficients C1 and C2, they were same because the electronegativity of the two atoms was same which were combining. Like in H2, the two atoms were, both of them were hydrogen. So, the electronegativity of both the hydrogen was same. So, as a result, the value of these constants C1 or C2 was same, or you can say that C1 was equal to C2. And these constants are those which give a minimum energy to psi AB. But when two different atoms are going to combine to form a molecule, in that case C1 will not be equal to C2 because the electronegativity of one atom will differ from the other atom. So here, if psi A and psi B are the wave functions of the two atoms, and if the electronegativity of psi B is greater than psi A, or the electronegativity of atom B is greater than electronegativity of atom A, then this psi B, it makes a greater contribution towards the bonding molecular orbital because of the lower electronegativity of atom B, and this psi A, it makes a greater contribution towards the anti-bonding molecular orbital because of the low electronegativity of atom A. So when we are going to make the atomic orbitals, in this case, there is going to be the energy difference between the two atomic orbitals. This is psi A, which is higher in energy, and this is psi B, which is lower in energy. And it is happening because the electron distribution between the internuclear region is not going to be symmetrical between the two atoms because there is electronegativity difference. So the more electronegative is the atom, it has more tendency to attract the electrons, therefore it is going to contribute more towards the bonding molecular orbital. When these two are going to combine, it will lead to the formation of this will be the sigma or the bonding molecular orbital, and this will be sigma star or the anti-bonding molecular orbital. And here we can clearly see the atom which has low electronegativity, it contributes more towards the anti-bonding molecular orbital, and the atom which has more electronegativity, it contributes more towards the bonding molecular orbital. Now, coming to some examples, the first example that I have taken is of nitric oxide. So here I am showing the molecular orbital diagram for nitric oxide. Now when nitrogen and oxygen, they are going to combine, the nitrogen, it has a total of 7 electrons and oxygen has 8 electrons. So when these two are going to combine, a total of 15 electrons will be there. So the order of filling will be the second one, that is without mixing of the 2s and 2p orbital, because the total number of electrons are greater than 14. Now in this case, you can see when we compare the electronegativity of nitrogen and oxygen, obviously oxygen is more electronegative than nitrogen, therefore the atomic orbitals of oxygen are lower in energy in comparison to the atomic orbitals of nitrogen. So here I am showing sigma 2s and sigma 2p orbitals. So when 2s and 2s of nitrogen and oxygen, they combine, they result in the formation of sigma 2s and sigma star 2s. Similarly, when the 2p is going to combine, the 2p orbital of nitrogen, it contains 3 electrons, whereas the 2p orbital of oxygen, it contains 4 electrons. And these are going to be the resulting molecular orbitals. The 2 electrons get filled into sigma 2p, then the they are going to be singly occupied first in the pi 2py and pi 2pz, and then the pairing will take place, and the 1 electron will get filled into either of the pi star orbital. So here it is getting filled in the pi star 2py. So when we calculate the bond order is calculated in a similar manner. The number of electrons in the bonding molecular orbital minus the number of electrons in the anti-bonding molecular orbital divided by 2. So total number of electrons in the bonding molecular orbitals are 2, 4, 6, 8 minus 3. So 8 minus 3 is 5 divided by 2, which comes out to be 2.5. So the bond order for nitric oxide is 2.5. And since the last electron which is present in the pi star 2py, it is unpaired, therefore the molecule is paramagnetic. Now, the question arises that N2 has a bond order of 3 and O2 has a bond order of 2, and NO, it has a bond order of 2.5, but still the stability of NO is less than both N2 and O2. Though it has greater bond order than oxygen, still the stability of NO is less than oxygen, because N2 is more stable because its bond order is greater than NO, and O2 is also stable in comparison to NO because the two atomic orbitals which are combining to form the molecular orbital, they are of the same energy, and when bonding takes place between the same energy orbital, it is going to form a strong bond. Whereas in the case of NO, there is appreciable gap between the atomic orbitals of nitrogen and oxygen. So, strong bond will not be formed. As a result, the stability of NO becomes lower than the oxygen molecule. Now, the next question comes that NO plus is more stable than NO. When we remove one electron from NO, it forms NO plus, and when we move one electron, this electron is getting removed from the anti-bonding molecular orbital, and since the electron which is present in the anti-bonding molecular orbital, it is of higher energy. So, we can say that higher energy electron is being removed from this system. As a result, the overall energy of the system decreases. Therefore, NO is more stable than NO plus, is more stable than NO. And the second thing, since this electron is getting removed from the anti-bonding, the bond order increases. The bond order of NO plus is 3 and NO is 2.5. So, again NO plus become more stable than NO because of these two reasons. Now, next molecule is hydrogen fluoride. The valence electrons which are present, hydrogen has 1s1 and fluorine has 1s2, 2s2, 2p5. Now, here we are going to focus only on the valence interactions, and we are going to accommodate for the differences in electronegativities between the two atoms, and there will allow the mixing between symmetry allowed states. So, there is going to be mixing between symmetry allowed states. Now, this is the MO diagram for hydrogen fluoride, that is the HF molecule. Since hydrogen has only one electron, this electron is a high energy electron, and fluorine has a total of 9 electrons and it contains only one electron which is unpaired. So, this hydrogen high energy electron, it does not interact or it does not form a bond with 1s and 2s of fluorine because of the high energy difference. Hydrogen atom 1s is high energy, this electron, and the 1s and 2s of fluorine, they are much lower in energy. Therefore, there is no interaction between 1s of hydrogen with 1s and 2s of fluorine. So, bond formation cannot take place. So, this 2p of fluorine is comparable in energy to the 1s of hydrogen, and in this case, this 1s of hydrogen combines with sPz or the pz orbital of the fluorine, resulting in the formation of sigma sPz and sigma star sPz orbital. Due to symmetry restrictions, the combination takes place with the pz 2pz orbital of fluorine. Now, in this case, the 2px and 2py since they are fully filled, they stay in the non-bonding state, and the 1s of hydrogen, it combines with 2pz of fluorine, and the 2 electrons get filled in the sigma spz orbital. This orbital is sigma sp Z, whereas the sigma star sp(z), the molecular orbital, remains empty. So, this is the atomic orbitals, hydrogen atomic orbitals and fluorine atomic orbitals, and this is the molecular orbitals of the HF molecule. And the bond order comes out to be 1 because the sigma orbital, sigma sp(z), it contains 2 electrons and anti-bonding orbital is empty. So, bond order will be 2 minus 0 upon 2 minus 0 divided by 2. So, it comes out to be 1. And since both the electrons in the outermost orbital, they are completely filled or they are paired, therefore, the molecule is diamagnetic in nature. So, HF, due to energy restrictions, since 1s is of high energy, it does not form a bond between 1s and 2s of fluorine, and due to symmetry restrictions, it forms a bond with the 2pz orbital of fluorine, and the 2px, 2py, they stay in the non-bonding state. Now, the next example is carbon monoxide molecule. Carbon monoxide molecule, in this case, carbon has a total of 6 electrons, whereas oxygen has a total of 8 electrons. So, after combining, the total number of electrons are 14 electrons. Therefore, the order of the filling will be the first one, that is with interactions with the 2s and 2p orbital. As a result, pi orbitals, pi 2p orbital will be lower in energy in comparison to the sigma 2p orbital. Now, in this case, these are the atomic orbitals of oxygen and these are the atomic orbitals of carbon atom. So, when 1s and 1s and the electronegativity of oxygen is higher than the carbon, therefore, the orbitals of oxygen will be of lower energy in comparison to the atomic orbitals of the carbon atom. So, 1s of oxygen combines with 1s of carbon, resulting in the formation of sigma 1s and sigma star 1s. Now, in this case, when 2s of carbon combines with 2s of oxygen, sigma 2s and sigma star 2s, they differ in energy more than it was expected. The energy difference between sigma 2s and sigma star 2s is more than it was expected. Therefore, as a result, the 2p orbitals, the pi 2p and sigma 2p, they become lower in energy in comparison to the sigma star 2s orbital. So, here when 2s and 2s they combine, this is the sigma 2s and sigma star 2s become higher in energy. As a result, these p orbitals, the pi 2px, pi 2py and sigma 2pz, they become lower in energy in comparison to these sigma star 2s orbital. This was confirmed when CO plus was formed from CO. When an electron was removed from CO molecule to form CO plus, the bond length of CO is the bond length of CO is 1.128 angstrom, whereas the bond length of CO plus is 1.115 angstrom. So, on conversion of CO to CO plus, there is appreciable decrease in the bond length, which indicates that the electron which is getting removed from the CO molecule, it should be an high energy electron, and the highest orbital or the antibonding molecular orbital which is filled is the sigma star 2s orbital. Therefore, it was concluded that the electron which is getting removed from CO, it must be from the sigma star 2s orbital. So, high energy electron, because the bonding electrons, they are lower in energy, and the antibonding molecular orbital which is highest mole which is filled is only of sigma star 2s. As a result, it was decided that this sigma star 2s must be higher in energy in comparison to the pi 2p and sigma 2p orbitals. Now, coming to the bond order calculations for CO molecule. In this case, the bonding molecular orbital has a total of 2, 4, 6, 8, 10 electrons, and antibonding has 2 plus 2, 4. So, 10 minus 4 by 2, which comes out divided by 2, comes out to be 3. So, bond order of CO molecule is 3, and since the outermost orbital contains electrons in the paired state, as a result the molecule is diamagnetic in nature. Thank you.